extensively about debug and trace interfaces of ARM Cortex-M based microcontrollers and trace outputs via them to analyze runtime behavior. Followed by that, we look closely at trace concepts and trace sources such as DWT, data watch point and trace, and ITM, instrumentation trace macrocell. At the end, there will be a live demo session presenting various trace use cases such as function trace, data trace, OS tracing and profiling, as well as printf-style event output on the console. So let's start with JTAG debug interface. JTAG is a common hardware interface that provides us a way to communicate directly with the chip. It is present on all ARM architectures or aside ARM. It requires minimum 4 essential signals: TCK, TMS, TDI, and TDO. JTAG is a bidirectional and synchronous debug interface which can be used for debugging and flashing microcontrollers. It's reasonably faster interface in the range of several tens of megahertz. Now I talk about SWD debug interface. SWD stands for serial wire debug. Actually, this could be an alternative to JTAG interface. SWD is an ARM specific bidirectional protocol or interface which can be used for debug and flash operations. The important thing is it uses only two signal lines, SWCLK and SWDIO. So a clear advantage of SWD over JTAG is it requires only two lines instead of 4 that we saw on JTAG, and this makes the hardware design and dimension much easier. So far we have discussed about debug interface. Now let's move toward trace interface. Cortex-M based microcontrollers support two types of trace interface, and parallel is one of them. A parallel trace port requires 1, 2, 4, 8 or 16 data pins and a clock. While using parallel trace interface, the width selection does have an impact on bandwidth and trace data. If I say width selection, it means 1 bit, 2 bit, 4 bit, 8 bit or 15 bit. Width selection can be determined by the user themselves, which can help them in hardware design. As an example, a S32K148 microcontroller, which runs at 112 MHz and can execute 70 million instructions per second. So if you select 1 bit width, then it can handle 7 megabyte per second of program flow data. If you select 2 bit width, then it can handle 14 megabytes program flow data. So the point is, user must know what they want to trace, what they are interested in. One important thing which we must keep in mind that in parallel trace pins are often multiplexed with input-output pin functions, so availability must be checked. In case of small package device where such pins are not available, there could be two possible solutions. First one is emulation adapter and the second one is SWO. So now let's have a look at SWO. SWO stands for serial wire output. It's an asynchronous single pin interface used to stream out data packet with certain clock rate. Though clocking and finding a correct communication rate is a challenge, but WinIDEA takes care of that. WinIDEA can calculate this data and it can be used directly. The catching part with SWO is mixed with TDO, and TDO is a part of JTAG, which is available on all the devices. Hence, you can consider it as a ubiquitous interface. But now, as TDO is used for SWO, JTAG cannot be used anymore. So the solution is use SWD, serial wire debug, instead of JTAG, because it does not require the TDO pin. Hence, the overall advantage is that SWO along with SWD has only used JTAG, that is, You need not to worry about muxing with any pin which might be used by the applications such as timer input output or SPI input output. Bit more information about SWO. So SWO supports hardware and software trace concepts. SWO can also be used as ITM console to send text or data, or record PC sampling to build an application profile. One of the important concerns with SWO is bandwidth, which brings some constraints. Program flow trace is not possible with SWO, but the bright side is data trace or OS trace is still possible. The important question is, how do we gather the data? In general, either by software trace or hardware trace. I'm not going into much deep about these two concepts, but in context of hardware trace, I talk about DWT. DWT module hardware comparators, which can not only detect data of interest, but they also capture the data from the CPU. Later, which is being forwarded to ITM, where trace messages are being formed and sent to the TPIU unit. In context of software assisted trace, I discuss ITM. It's an ARM core site IP which can generate trace messages. These trace messages can be generated upon either by simply writing data to the dedicated ITM stimulus port or received trace data from the DWT module. At last, trace messages are being sent to the TPIU unit. Once the trace messages is being sent to the TPIU, again the trace interface, that is parallel and SWO, comes in picture, which decides the output bottleneck. In next two slides, we know more about DWT and ITM module. The DWT implements four hardware comparators, which can serve either as on-off triggers to ETM instruction trace or as a data watch points. In the latter case, they can either stop the CPU, I mean as a breakpoint, or they can capture the data without stopping the CPU. Using these four hardware comparators, four global data variables can be traced out. But if a local data variable or more than four data variable is supposed to be traced out, then ITM stimulus port is a solution. We will see that in the later part of this webinar. The ITM module has 32 stimulus port, and the generated output message contains the core ID, stimulus port ID, and the data written to it. Data width could be 8, 16, or 32 bit. One of the way to generate trace message by ITM is writing data to the ITM stimulus ports. The data written to these ports are output to the trace tools. Different ITM stimulus port can be assigned to signal different types of trace information. In case of multi-core application, each core has its own dedicated private ITM and stimulus port. Hence, it can be accessed via its own private bus, and it does not put any additional load on the system bus. The big advantage here is each core sees the ITM at the same address because this address is private to each core and it is not part of the system memory map. Therefore, the instrumentation code does not need to care about which core executes the code. Now, this is the time for live demo part of this webinar. But first, let's have a look at SWO trace tool setup. I use IC 5700 and a core site 10-pin connector. The microcontroller used are S32K148 and S32G. Both are Cortex-M based microcontrollers. I will let you know when I am using what with a particular combination of OS. The 10-pin pin connection can be seen here. I use SWD as debug interface and SWO as trace interface. These are the use case which I am going to demonstrate right now. I have segregated live demo use case into two parts. First one is using DWT data trace without instrumentation, and the second is using instrumentation trace via ITM. So let's go to WinIDEA. I have already opened my workspace. I'm using 9.21.11 WinIDEA version. Let's have a look at some other required WinIDEA configuration. I have selected here my MCU. If you are using an older version of WinIDEA, then this configuration might looks new to you. Then please see our webinar about 9.21 start of new decade on our YouTube channel, and then you get more familiar with 9.21 WinIDEA version. Here I have selected SWD debug interface, SWO trace interface, and for the SWO you must define clock and prescaler. I will show you how to find it out these details. Press OK. I have already downloaded, so I will just give symbol download. You see my application is running. Let's stop this. Go to hardware, tools, and here you can click on SWO calibration, and then you can press start. So you can see WinIDEA has already automatically calculated it for you. Press this, press apply, press close, and give a symbol download. Let's run this. So application is running. We will cross verify. So hardware, CPU options, SoC, and then you can see the value is present here. So I will press cancel. The next two use cases are global data variable trace and OS trace using DWT data trace. I will be using S32K148 microcontroller, and I'm using an AutoSAR based ETAS OS sample project. So now let's do a global data variable trace. For that I need to open the analyzer window. I have already opened it here, but you can go to view and click on analyzer to open this. I will show you how to create a new analyzer configuration for each use case. For this particular use case, I will be creating a new analyzer configuration in three ways. I mean using automatic, wizard, and manual. And afterward, for rest of the use cases, either I will just use automatic or existing analyzer configuration. Let's start with wizard option. So give a proper name. Press OK. You need to select here process. Select trigger immediately. Go for data access and then select write. And then you need to select the variable which you are interested in. So press here. I want to trace I counter, so I will select this. Press next and press finish. Now this window will appear, so we go to DWT core 0. This variable has been already added and you need to select sample data value here, which has been already selected. Go to ITM and just enable this module. Now press OK. Now click on this hammer. You need to select the process, click on new, select here app core 0, press OK. Then you need to go to profiler, select data, press on new, select trace, core 0, change it to regular variable, press OK and press OK. And now through wizard option you have already created a new analyzer configuration. So let's run the software and let's run this. So you can see the results on profiler timeline, and meanwhile you can see on the trace window as well. Now we will do the same by creating a new analyzer configuration, but we will follow this manual approach. Select manual, press OK, go to DWT, enable DWT module, and then you need to select write access, select variable iCounter, change it to sample data value, go to ITM, enable this, press OK. Select on hammer, select the process, deselect these two. We are interested in data, so press new, trace, iCounter, core 0, regular variable, press OK, and now we run again. We should expect the same result. So you see here, you can see the iCounter on the profiler timeline and parallelly on the trace window. Now we do the same configuration. We are going to create the same configuration again, but through automatic way. So data trace auto, select here automatic, press OK. Now you need to add the process here. Go to profiler, add data, trace, iCounter, core 0, regular variable, press OK, press OK, and now let's run this. So you see here again you have iCounter on the profiler timeline and trace. You can see the trace messages on the trace window. So this is how you do a global data variable trace using DWT hardware comparators. Now let's move to our second use case where I will be doing OS trace using DWT data trace. But first we will have a look at our OT file. So this is our OT file, pizzapronto.ot, and here you can see these are the tasks. Then these are the ISRs, and if you scroll a little bit down, then you can see this is the variable OS running task, which you need to trace out to find out the running task, and in the similar fashion OS running ISR is the variable responsible to trace out the running ISR. But In order to make our WinIDEA aware, we must add this OT file in our WinIDEA. So we go to Debug and then Configure Session, click on Edit, click on OS, then here you need to select an OS, press on Configure, and then the file is OT file, so you can select OT here, and then you need to give the file which you are supposed to add. So here our file is pizzapronto.ot. I will select open this and then press OK, and then press OK, and then you can give a symbol download. Now let's do a new configuration for this use case. So create new configuration, give here a name, select automatic, press OK, add a process, go to profiler, uncheck code, and now if you see here, select here OS objects. If you click on running ISR, then you can see the running the responsible variable here, OS running ISR, and the two ISR. Similarly for the task or OS running task here. So now you press OK, and WinIDEA will automatically configure two DWT hardware comparators to trace out this OS running task and OS running ISR variable. So now let's run this. Let's stop. So now you can see the results. Here you can see the running tasks. Here you can see the running ISR, and similarly on the trace window you can see the two variable which has been traced out. Apart from that, you can have a look at profiler statistics as well. Like net time, gross average time, or if you click on, just give a right click and click on properties, then you can see all the details like time between consecutive entry exit, time spent in the body of the functions, and so. So this is how you perform OS tasks in ISR using DWT data trace. Now I'm going to perform instrumentation trace via ITM use case, and we start with OS trace. I'm going to use S32G microcontroller as a single core application with Electrobit Tresor Autocore OS. Here I will be using different ITM stimulus port to trace out the OS tasks in ISR and their states as well. I have created a profile XML file, so let's have a look. This is the profile XML. Task states are defined here. ISR states are defined here. Tasks are defined here. So does the ISRs. ITM stimulus port 1 is used to signal tasks and their states. ITM stimulus port 0 is used for ISRs. Let's have a look at ITM configuration. You can see the ITM channel 0 and 1 defined here. All the task state information will be passed through defined ITM channel. Similarly for ISRs. Let's add profiler XML file to WinIdea. Let's open Analyzer window and create a new configuration for this use case through manual option. Let's configure ITM module. Global timestamp is used and stimulus port as all. You can select the used ones too. We'll add the process and configure the profiler data area for ITM channels and OS objects for tasks and ISRs. You can see the defined ITM stimulus port 0 and 1 in the object expression field for the tasks and ISRs. Let's do a download and run the analyzer. You can visualize the tasks and ISRs on the profiler timeline. You can also visualize the task states. And this is how you perform OS trace using ITM stimulus ports. Now I'm going to perform local data variable trace and runnable profiling using code instrumentation via ITM. For runnable profiling or function profiling using code instrumentation, concept is to mark the entry and exit, and every entry is marked with a unique data value, whereas exit is always 0. This unique data will be passed through an ITM stimulus port. I'm going to use S32K 148 microcontroller for this use case. This is the generic macro to configure the ITM for Cortex-M based microcontroller. These macro are specific for runnable profiling, and ITM stimulus port 4 is configured. This is specific for local data variable trace, and ITM stimulus 5 is configured. Here I have some runnables, and you can see I have marked the entry and exit. And this value is defined here in my header file for all the runnables. Similarly for other runnables. For local data variable trace, this is the function, and here I have defined a local variable and I am passing it through this defined macro. Let's create a new analyzer configuration for this. Enable this and select the channels 4 and 5. Press OK. Select ITM and channel 5 for local data. You can give a name. And add here the define file. And now let's run this. So you can see the runnables and local data on profiler timeline. After you zoom in, you can see runnable A is calling A1, A2, and A3. Here runnable B is being called, and B1 has been executed, and B2 is calling B3, and so on. And here you can see the local data. One last time, we go back to the presentation to discuss the use case printf to terminal. The aim of this use case to redirect the printf output to ITM and display the text information in WinIDEA. Traditionally, printf-style debugging uses user interface, for example UART. But there is a possibility that UART has been already used. So instead of UART, we can use ITM to redirect the messages. There are few steps to execute this use case. First step is to create a library extension file. Basically, input-output functions, example printf or scanf, are called low-level functions to perform the actual input and output. It largely depends on compiler or library being used. I'm using GCC, which uses a special version of Red Hat newlib library. This newlib calls the write or read function, or in other words, getChar or putChar to implement character output. In this diagram, we see user code will have ITM sendChar or putChar, which will write to ITM channels. Basically, ITM sendChar or putChar, you can give your name as per yours. In normal way, it goes to trace analyzer, but here it will be redirected to WinIDEA terminal. So let's go to WinIDEA and see how did I perform this. So this is my stuff file syscall.c. Basically, syscall.c file implements right? There are few specific linker which you need to add. So you must add this. Now let's open the WinIDEA terminal. There are a few settings which you need to done. Go to options, select your debugger, and then click on configure. Select trace channel, then go to advanced. Select here selected or all, and you use ITM channel 0 because ITM channel 0 is used for text. Press OK, press OK, press OK. Before running this application, let's have a look at this implementation. So I'm using SWO print string, which will display the I counter and its value on the terminal window. This is the implementation of SWO print string. Let's download. Let's run this and connect. So you see here I counter and its value is being sent to this WinIDEA terminal. So at this point, I end the technical part of this webinar. So thanks a lot. Thanks for your time and listening.
Thanks, Manish, for your demonstration. This was very interesting, and now we all know why it is ubiquitous, and we learned a new word. So at least I did.
You're welcome.
Thank you.
Yeah.
Before we continue, I would like to remind the audience that it's now time to download the presentation by clicking the cloud symbol top right of the screen. Feel free to do that. We don't have any questions so far, so I would like to take the chance to raise some questions, Manish, if you don't mind. And
No.
I would like to refer to the two demos you had. So what is the advantage of the data trace via ITM compared to the WT, to put it in a nutshell?
Okay, so I mean, DWT module has 4 hardware comparators. So you can trace out 4 global data variables or 4 different global data objects at a time. But if you look at ITM, though observing objects through ITM is limited through instrumentation code. I mean, limited to 32 because of ITM has 32 stimulus ports. But in our WinIDEA, we can mark which stimulus port is taking care of which data object. Doesn't matter it is a global or local. So this is one of the clear advantages of ITM over DWT when you want to go for more than 4 data variable trace or you want to trace a local data variable.
So basically, it's much more powerful, and if ITM is available, then the user should use ITM, right?
Not every case, but yeah, it's recommended.
but for details, always check with our engineers, and
Yeah.
then we will help you further.
Yeah, definitely.
Wonderful. I also would like to come again to the demonstration to the printf feature. When I think back what you showed before, the ITM, the DWT, the blue box needs to be equipped with a so-called trace activation key. So as soon as you want to use the analyzer, you need a trace activation key. You used now for the printf feature the WinIDEA console. Does the user also need a trace activation key then?
No, you do not need a trace activation key. Maybe you can talk, I mean, you can put more insight about license and trace activation key. I would request.
Yeah. So the difference really is you don't use the analyzer, so you don't need a trace activation key, and you don't need anything else except the debug activation key and the adapter that you can use the printf feature.
Yeah.
Wonderful. Another one, I would like to come to the SW output. What is the maximum clock speed of this SW output?
Yeah, definitely, it's a good information to know about. But directly jumping to the answer, SWO interface is an asynchronous interface. I mean, you do not have a clock line, but you do have a data output line, you know. So, I mean, so the trace sources, I mean, the receiver need to be synchronized with the output data stream. I mean, by performing a clock recovery and so on. And by nature also synchronous interface is bit better than asynchronous. So at the moment our IC 5700 supports SWO data rate of 40 megabytes per second, but we continuously work on to improve this. Earlier it was 10 megabytes per second, now it is 40, so definitely we are on the right track.
Absolutely.
Yeah. Yeah.
Yeah, thanks for explaining that and
Yeah.
also giving an insight
Yeah.
into the improvements we are doing.
Yeah. In future it's always better.
Yeah, definitely.
Yeah.
I have one last question. So what is the typical code overhead of the ITM instrumentation code, for example, for runnable and function profiling?
Yeah, very good question, I would say. And
Thank you.
yeah, and many user ask this question, you know. But for this question, first we need to understand how ITM instrumentation code is being implemented, you know. So basically instrumentation code is implemented as C macro. So the codes gets inlined with the every instance of C macro. So if you look at instrumentation code, then basically it consists of few shifts or instruction, and at the end there is a load instruction to the ITM stimulus port. So overall, I would say hardly 5 to 10 assembly instruction. So it's negligible, and definitely it's recommended. Definitely it's recommended. Yeah.
Cool. Thanks for the explanation. Thanks,
Yeah.
Manish. I think we have no questions left. Thanks, Manish, again. Thanks for your time. Thanks for sharing your knowledge with us.
It's my pleasure.
And before we are coming to the end, I would like to give you some general information. We would appreciate if you leave us your feedback in the polls section. So we would like to improve our webinars, of course. And if you have any topic suggestions, please feel free to send an email or drop it into the question tab. Check out also our online trace tutorial, our application notes, and also our webinars on the iSystem YouTube channel. Manish was also referring to the one or the other webinar, so definitely check it out.
Yeah.
And if you want to get information, for example, the webinar invites automatically, feel free to register to the newsletter, and please make sure also to confirm the confirmation email because German GDPR requires that. Then, as I already said, if you have questions afterward, please feel free to send us an email to webinar@isystem.com or to the sales or tech representative. That's it for today. Thanks, Manish, again. Thank you for watching. Thank you for attending. All right. Thank you again. Bye, everyone, and take care.
Bye.